There's a deep link between the universe, the grand scheme that's unfolding, and beings like ourselves. Somehow the universe has become self-aware. It's engineered the emergence of comprehending, thinking beings like ourselves who can come to know the universe.
Some people marvel at the fact that the universe has, over billions of years, given birth to beings who can appreciate its complexity.
We need to look at the hidden subtext of nature, the mathematical relationships that underpin it, forming a sort of shadow world. Some people think of this as like a cosmic code.
Regardless of whether or not they believe in God, most scientists agree the cosmic code appears to exist.
I'm on my way to talk to Stephen Hawking about some of the questions we are both still asking. I want to ask him his views on evolution. As a physicist, does he think that the origin of life on Earth is just a happy coincidence?
The existence of the Earth and the properties that made it possible for biological life to develop depend on a very fine balance between the so-called constants of nature. If they were more than slightly different, either planets like the Earth would not occur, or the chemical processes necessary for life would not take place. One might take this as evidence for a divine creator, but an alternative explanation is what is known as the multiverse. The idea is that there are many possible universes. Only in the small number of universes that are suitable will intelligent beings develop and be able to ask the question, why is the universe so carefully designed?
Everything in the universe is determined by the fundamental forces of nature. The strengths of those forces are characterized by numbers called fundamental constants that are so sensitive that if they changed by just a little bit, the universe as we know it wouldn't be here. For example, if the rate of expansion of the universe right after the Big Bang had changed by 1 part in a quintillion is 1 with 18 zeros after it, the universe would continue to expand or collapse back on itself, and none of this would be possible. To illustrate just how small a number 1 part in a quintillion is, imagine all the grains of sand on this beach. In fact, imagine all the grains of sand in all the world's beaches. That number's probably somewhere around a quintillion. In this analogy, if all that sand represented the rate of expansion of the universe right after the Big Bang, how many grains of sand would I need to add or subtract to wreck the universe? Just 1 grain, 1 in a quintillion. That's how precise things had to be for us to be here.
Physicists believe that when time began, at the moment of the Big Bang, matter and antimatter were created in equal amounts. And based on recent measurements made at CERN Laboratory in Switzerland, it seems there is perfect symmetry between the two, which they say implies that our universe should not exist. What? Okay, here to talk about this perhaps disconcerting discovery is CBS News science and futurist contributor and theoretical physicist Michio Kaku. All right.
Antimatter is the mirror image of ordinary matter. It's extremely rare. If I had some in my hand, it looked like ordinary matter. It has the same chemical properties, except if I touch it, it would explode and destroy all of New York City, parts of Connecticut and New Jersey. Every Star Trek fan knows that this is the greatest energy source in the universe, matter-antimatter collision.
Okay, all right, so that's it. Well, what is it about this symmetry between matter and antimatter that, leads CERN's physicists to this conclusion that we shouldn't exist, the universe shouldn't exist?
Well, at the incident of the Big Bang, there should have been equal quantities of matter and antimatter, which annihilated, driving the Big Bang. So, by rights, we shouldn't be here.
Right.
Because we have more matter than antimatter in our sector of the galaxy. We've looked for anti-galaxies. We've looked for anti-planets. We don't see any.
I don't even understand what that means, but okay, go ahead. Antimatter, anti-planets, because they would be made up of anti.
That's right. In fact, we see no evidence of that at all. So physicists say by rights we shouldn't exist. This means that at the instant of the Big Bang, there was a slight overabundance of matter over antimatter, and here we are as a consequence.
All right.
Now, why?
Yeah, all right. Well, tell us more about these experiments that CERN is doing to answer, or at least try to answer, these questions.
Well, they take an atom smasher and they take the energy out of it and put it into a bottle. It's called a magnetic bottle. You can actually trap anti-hydrogen, anti-electrons going around anti-protons. And when they measure the property of anti-hydrogen, it's exactly like ordinary hydrogen, except, of course, they would annihilate it if they touched each other. And that's so frustrating. You want to tear your hair out.
Right.
They were looking for an asymmetry between matter and antimatter. They find none. And so that's the mystery. Why do we exist at all? By rights, we shouldn't be here.
Yeah.
By rights, we should have been disintegrated at the instant of the Big Bang.
Yeah.
The apparent fine-tuning of the universe is one of the hottest and indeed most controversial topics in our intellectual life today. Among physicists, argue about it among each other, philosophers, theologians, and then philosophers, theologians, and physicists all together. I want to get your sense, first of all, about the legitimacy of the question in terms of, is the universe fine-tuned, particularly the initial condition?
Well, the universe is certainly fine-tuned in the sense that the initial state of the universe was extraordinarily special. Now, there's fine-tuning in the origin of the universe, which has to do with the second law of thermodynamics. It has to have been extraordinarily precise, and in fact, it has to have been at least as precise as 1 part in 10 to the power 123. Now that's
an extraordinary number.
It's a ridiculous number, yes. That's right. And it's nothing like, people worry about the constants of nature. You see, you want to fix those constants. Okay, they're just a few numbers. 20 numbers maybe. Yeah. And those have got to be fixed to, I don't know, just a certain amount of precision. And that's nothing by comparison with this number. The precision that we see in the initial state of the universe completely dwarfs any of these other considerations.
And that level of precision is so impossible to conceive of as from some random point of view. I mean, that's not something that you can achieve in a random fashion under any. I mean, in infinity you can do anything, but obviously, but that's a.
It's no explanation. I mean, that's right. I mean, you can't say, well, there are lots of universes, and out of that particular one, which we happen to be in, that number was that thing. Well, no, it doesn't explain it. You don't get anywhere close to that number.
Right. What is the implication then in terms of the generation of such incredible precision? Can the argument of multiple universes achieve that?
Well, I don't think any of these are going to, you see, it's such an improbable. We're talking about how special the Big Bang was.
Yes.
Now, you could imagine other Big Bangs which weren't so special. But, I mean, you can have other Big Bangs not so special, but that's not what we've got.
Yeah.
See?
And we're here in this one.
We're here in this one. We could have been here equally well in zillions of the other ones, you see, which weren't so special. You could have a universe which is special in our neighborhood. Our galaxy could be just as it is, but the distant universe would be different and not special out there. And that's much more likely. If you're just talking about probabilities, all these other alternatives are far more likely than the one we see, which is saying we're here and that's why the universe is as special as we see it, doesn't go anywhere to explaining the specialness of the Big Bang. It's just, it gets you nowhere because we don't need the universe to be that special for us. It's not any use to us at all why the distant universe is incredibly special and why it came from a Big Bang, which is just part of the Big Bang, which is just as special as the part we came from. And you can't say, another argument, you can't say, well, okay, you could have got lots more people by having a bigger universe. That doesn't work either, because there's lots of cheaper ways of making lots more people. You make lots of universes. And it's far cheaper in the sense of improbabilities, that's to say it's far more probable, to make lots of universes with a few people in each one than to make one universe full of people. I mean, that's just a simple way of saying it.
In a sense, this is an even deeper mystery than the anthropic people normally put out for us.
Yes, it is, yes. No, it needs a scientific explanation. It needs a good physical theory. to say why the Big Bang had that nature that it did. And we have no theory which really explains that. I mean, people usually say it's quantum gravity. No quantum gravity theory I've ever seen incorporates the asymmetry in time, which is necessary to explain why the Big Bang had this special nature, and not the singular states which come from black holes, collapses, and so on. There has to be something asymmetrical, because the second law of thermodynamics is asymmetrical. And any quantum gravity theory, which is going to explain why the Big Bang has this special structure, has got to have that in it. And no theory I've ever seen has that character.
You see, Einstein believed in another God, the God of Spinoza, the God of Leibniz, the God of order, harmony. The universe could have been random. It could have been chaotic. It could have been messy. But the universe is actually quite elegant, quite simple, and in fact is gorgeous. You can put the laws of physics as we know them on a simple sheet of paper. Amazing. Didn't have to be that way.
The laws of physics, the nature of the physical environment, and the physical constraints of replication and mutation ensure that in a universe with the basic physical constants and laws of this one, carbon-based life forms with opposable digits, eyes in their heads, and large brains are bound to come into existence. But Conway Morris argues that the landscape of biological form, be it at the level of proteins, organisms, or social systems, may in principle be almost infinitely rich, but in reality the number of roads through it may be much, much more restricted. There are only some feasible roads through protein hyperspace because of physical constraints that force a convergence of paths upon mutating organisms. There may be many paths to take, but they will converge on a number of solutions that are likely to be repeated wherever life evolves. Conway Morris's view is quite subtle. Even though, he says, the possibility of intelligent life is already laid down in the basic structure of the universe, the deep structure of the universe indicates life's inevitability. Nevertheless, life may be very rare or even unique to this planet. That is because conditions for its existence need to be just right. We would need planets of the right size and distance from their local stars, with large satellites, some protection against stray comets, and an atmosphere to ensure just the right amount of safe radiation from the nearest star, which also needs to be just at the right stage not to fry or freeze the planets in question. These conditions are so various and so precise, and need to be so exactly correlated.
Why does mathematics work? Think about it. Mathematical entities like numbers, sets, and equations are non-physical and abstract. They can't cause anything. Yet, for some reason, the physical universe operates mathematically. As Galileo put it, the book of nature is written in the language of mathematics. Scientists do not use mathematics merely as a convenient way of organizing the data. They believe that mathematical relationships reflect real aspects of the physical world. Science relies on the assumption that we live in an ordered universe that is subject to precise mathematical laws. Thus, the laws of physics are all expressed as mathematical equations. For example, Pythagoras discovered that when a vibrating string is shortened by half, it plays the same note 1 octave higher. Isaac Newton's observations led to his discovery of the law of gravity, a mathematical relationship expressed as a simple equation that enabled us to enter the space age. Mathematics enabled astronomers to pinpoint the location of a previously undiscovered planet. And James Clerk Maxwell used mathematics to predict the existence of radio waves. Albert Einstein, working with theoretical mathematics developed 50 years earlier, formulated his general theory of relativity, a pillar of modern physics. His calculations were later confirmed during a solar eclipse, when Arthur Eddington observed light from distant stars bending around the sun. Then, Peter Higgs used mathematical equations to predict the existence of an elementary particle. It took 48 years, billions of dollars, and millions of man-hours for experimental scientists to finally detect the Higgs boson. How do we explain the astonishing applicability of math to the physical world? In 1960, the Nobel Prize-winning physicist and mathematician Eugene Wigner published an article that stunned the scientific community entitled the unreasonable effectiveness of mathematics in the natural sciences. Wigner concluded that the effectiveness of mathematics is a miracle, which we neither understand nor deserve. Why is mathematics so effective? Philosophers who address this question fall into two camps. Naturalists, who believe that all that exists concretely is space-time and its physical contents. They exclude supernatural causes. And theists, who believe in a God who created the universe. Naturalists cannot provide a reasonable explanation for why mathematics applies to the physical world. It's just a happy coincidence. But this is no explanation at all. At most, naturalists can say that it's not surprising that math applies to the world, because the world itself just happens to have a mathematical structure, so of course mathematics applies to it. But this explanation is unsatisfactory for two reasons. First, a great deal of mathematics in science cannot be physically realized. For example, imaginary numbers and infinite dimensional spaces. Although these concepts are useful, physical reality cannot possibly have the structure they describe. And second, this answer still doesn't explain why the physical universe has such a stunningly elegant mathematical structure. By contrast, for theists, mathematics works so well in the physical world because God has chosen to create the world according to the plan He had in mind. Mathematics and physics work so well together because the same mind that designed the universe on a mathematical model also built the universe on the same mathematical model.
To the teleological argument from the fine-tuning of the universe. Scientists have been stunned by the discovery that the existence of intelligent, interactive life depends upon a complex and delicate balance of fundamental constants and quantities, like the gravitational constant or the amount of entropy in the early universe, which are fine-tuned to a degree that is literally incomprehensible. Now, there are three possibilities debated in the literature for explaining the presence of this remarkable fine-tuning: physical necessity, chance, or design. The question then is, which of these three alternatives is the most plausible? On the basis of the evidence, we may argue, 1, the fine-tuning of the universe is due to either physical necessity, chance, or design. 2, it is not due to physical necessity or chance. 3, therefore, it is due to design. Consider then the first alternative, physical necessity. This alternative seems extraordinarily implausible because the constants and quantities are independent of the laws of nature. The laws of nature are consistent with a wide range of the values of these constants and quantities. For example, the most promising candidate for a theory of everything to date, superstring theory or M theory, allows a cosmic landscape of around 10 to the 500th power different universes governed by the present laws of nature, so that it does nothing to render the observed values of the constants and quantities physically necessary. So what about the second alternative, that the fine-tuning is due to chance? The problem with this alternative is that the odds against the universe's being life-permitting are so incomprehensibly great that they cannot be reasonably faced. In order to rescue the alternative of chance, its proponents have therefore been forced to adopt the hypothesis that there exists a sort of world ensemble or multiverse of randomly ordered universes, of which our universe is but a part. Now comes the key move. Since observers can exist only in finely tuned worlds, of course we observe our universe to be fine-tuned. So, this explanation of fine-tuning relies on 1, the existence of a specific type of world ensemble, and 2, an observer self-selection effect. Now, this explanation, wholly apart from objections to 1, faces a very formidable objection to 2, namely the Boltzmann brain problem. In order to be observable, the universe need not be fine-tuned for our existence. Indeed, it is vastly more probable that a random fluctuation of mass energy would yield a universe dominated by Boltzmann brain observers than one dominated by ordinary observers like ourselves. In other words, the observer self-selection effect is explanatorily vacuous. As Robin Collins has noted, what needs to be explained is not just intelligent life, but embodied, interactive, intelligent agents like ourselves. Appeal to an observer self-selection effect accomplishes nothing because there's no reason whatever to think that most observable worlds, or the most probable observable worlds, are worlds in which that kind of observer exists. Indeed, the opposite appears to be true. Most observable worlds will be Boltzmann brain worlds. Since we are presumably not Boltzmann brains, that fact strongly disconfirms a naturalistic world ensemble or multiverse hypothesis. It seems then that the fine-tuning is not plausibly due to physical necessity or chance. Therefore, we ought to prefer the hypothesis of design. In summary, then, it seems to me that the evidence of contemporary cosmology provides significant support for key premises in two philosophical arguments for conclusions having theological significance. Thus, the existence of a creator and designer of the universe seems to be significantly more probable in light of contemporary cosmology than it would have been without it.
Michio Kaku is a theoretical physicist. As a pioneer of string theory, which proposes the world is actually nine-dimensional, he believes scientists need to keep an open mind.
We physicists are conservative revolutionaries in the sense that we have to be open to all sorts of crazy, bizarre phenomena. Who would have thought that there's something called radioactivity? Who would have thought that we would have quantum forces? So we have to be open to these things. The most successful physical theory of all time is called quantum mechanics, the theory of the atom, because it's based on the idea of probabilities, that you don't really know where an electron is, and electrons can exist in some sense in multiple states at the same time.
The fuzzy nature of subatomic particles might just provide a way to explain the sixth sense. Erwin Schrödinger, one of the founders of quantum mechanics, designed a thought experiment to drive home the strange rules of his theory. Let's say we put a cat and a vial of poison in a box. We add an atom of radioactive uranium and a Geiger counter. If the uranium decays, it sets off the Geiger counter, which then releases the poison and silently kills the cat. Before we open the box and look, we can't actually know whether the uranium has decayed or not, since radioactive decay is a probabilistic quantum event.
Here's the question. Is the cat dead or alive? Well, according to quantum mechanics, the cat is neither dead nor alive, but the sum of the two states. Well, at that point, you say, well, that's nonsense. That's preposterous. How can you be both dead and alive simultaneously?
Schrödinger's cat was supposed to show that nothing in this universe is certain until someone makes a measurement. But another pioneer of quantum mechanics, Eugene Wigner, believed it could teach us something else about the working of the universe. That consciousness controls everything.
Wigner said, let's take it one step farther. If I, a human being, looks at the cat, I am conscious. Therefore, consciousness determines existence. At that point, Einstein went ballistic and said, what? You're saying that the fact that you are a conscious being determines the fact that the cat is alive? Answer is yes. And Wigner made one more step, and that is, how do I know I'm alive? You see, the cat and me, we're part of the same universe. If I don't know the cat is alive or dead, I could also be dead at the same time and not even know it. So who determines that I'm alive? Well, Wigner's friend looks at me, I look at the cat, and we exist. But then who looks at Wigner's friend? And there's an infinite chain of people looking at people, looking at people, until finally you hit cosmic consciousness. Some consciousness that's ethereal, that envelops the universe, which looks at us and says, aha, the cat is alive.
Wigner believed that consciousness is an inextricable part of reality, that nothing really happens in the physical world unless a conscious mind observes it.
What are your thoughts on questions of spirituality and religious questions and religious explanations for these kind of things and so forth?
Well, there is a loophole in the quantum theory.
Yeah.
As I said before, there's a quantum transition between nothing to these small bubbles.
Rather.
These bubbles start to expand.
Yeah, there's a big quantum leap from nothing to something.
Something, right.
Yeah.
However, even within the quantum principle, and I'll work in the environment in a second.
Oh, we'll get to it.
Right?
Yeah.
There is a loophole,
Yeah.
and that is that in order to make sure that you know the state of an object, like whether or not an atom has decayed or not,
Yeah.
or whether I'm even sitting here at the table,
Yeah.
you have to make a measurement.
Yeah.
And before you make a measurement, you don't really know whether the person is really there or not. There's a famous experiment of the Schrodinger's cat, which a lot of spiritualists have rediscovered in the last 10 years. If I have a box with a cat in it, and the cat is attached to a gun,
Yeah.
and the gun is attached to a Geiger counter, and the Geiger counter is attached to uranium, you don't really know whether or not the uranium atom is going to decay, set off the Geiger counter. The Geiger counter is going to set off the gun and kill the cat. If the cat's in a box, the quantum mechanical description of the cat is I have to add the live cat and the dead cat. The cat is neither alive nor dead. The cat is represented by a mathematical wave function, the sum of a dead cat and a live cat. When you open the box, you make a measurement. At that point, the cat is dead. Now, the question is, before you open the box, is the cat dead or alive? And the answer is, and this will shock you when you hear about this.
I'll get ready. Let me hold on tight. Yes.
The fact is, quantum mechanics says the cat is neither dead nor alive.
Uncertainty.
Uncertainty.
Principle.
Right.
Heisenberg. No.
Right. Now, the question is, if you have to observe something to make sure the cat is either dead or alive, this means, of course, that somebody has to do the observing.
Yes, right.
Consciousness has to open the box. Now, the question is, therefore, was there consciousness before humans?
Yeah. Oh, well, okay.
Now, Einstein asked this question. He said, this is ridiculous. He didn't believe in the quantum theory. We now know this is, of course, Einstein's great mistake. And he had a very famous interaction with a guy named Abraham Peiss. They were walking down the street one day, and he said, look at the moon.
Yeah.
And Abraham looked at the moon, and he said, I see the moon. And he said, do you believe that the moon exists only because a mouse can look at it? Mice have been on the earth before humans.
That's right. Yeah.
Mice have looked at the moon. And he said, do you think the moon sprung into existence just because a mouse looked at it? Now, Einstein was very puzzled about this. Now, of course, the average person hearing this for the first time thinks that scientists have finally gone wacko, that this, of course, is the end of physics. Scientists have finally gotten off the deep. They're mad. But actually, this has been tested experimentally. We have atoms. Atoms like cats that are neither dead nor alive. And before you look at the atom, you cannot tell whether they're dead or alive, whether they have decayed or whether they're still there or not.
Yeah.
Okay? So in fact, the act of observing means the thing springs into existence. So in other words, did the dinosaurs really exist? Okay, now of course every scientist will say, every non-quantum scientist will say, of course the dinosaurs exist. We have bones.
We do.
Right? We have bones.
All over the place.
However, a quantum physicist, and this is all serious now, will say that there is a wave function of a world where there are no dinosaurs, or dinosaurs that are still alive, or there's a wave function of dinosaurs that have bones. And before you look at the bones, you can't tell that it is physically impossible to determine whether or not there were in fact dinosaurs. Okay? Now this, of course, means that physicists have to confront the question of consciousness. And that is rather uncomfortable. We physicists don't like to talk about consciousness, especially consciousness other than human consciousness.
Yeah.
In other words, does the universe exist just because we look at it? Does the moon exist because a mouse looks at the moon?
Yeah.
Do dinosaurs' bones exist because I looked at the dinosaur bones? What about dinosaurs before humans?
Yeah.
However, the quantum theory, and this is what bothered Einstein, brings us back to the question of who observes. can you observe without humans? If so, does that mean that necessarily you have God, which some physicists say? Eugene Wigner, winner of the Nobel Prize, said that this essentially proves the existence of God.
Matter originates in accordance with laws of nature, quantum laws, which must have existed before there was any matter, because the matter comes into existence in accordance with the quantum laws. So it cannot be true that they think the laws just describe how matter acts. On the contrary, the laws tell matter how it's going to act, and the laws actually create matter. You know, some of my colleagues like to talk very misleadingly about these days we believe in the bootstrap theory of the universe. And the bootstrap theory is the universe pulls itself into being by its own bootstraps. In other words, out of nothing. You get creation out of nothing. But it's not nothing. You've got the laws of quantum physics, and they're not matter either. And they exist in order to produce the universe. So modern physics has got itself into a state where it cannot be materialistic. That's the irony of materialism, that materialists think they're being scientific, but quantum physicists say, well, actually, matter is very mysterious sort of stuff, and it originates from something beyond the material.
Matter is really an appearance of mind. Using the word mind rather broadly, something conscious, something intelligent. But consciousness is the important point. So there may be a material world, but if there is, it's an expression of an underlying and more real and more truly existent conscious world. And a lot of quantum physicists, not all, but I think the majority, see consciousness as much more important than matter. So let's just start with that thought of idealism, that consciousness is an ineliminable, you can't get rid of it, part of reality, and that probably it's more fundamental than matter is. Indeed, matter is nothing but an appearance of some form of consciousness. Who says this? Oh, right, let me give you some names. Heisenberg is probably the person, well, he is the person who formed the first quantum theory in 1925. What Heisenberg said in 1925 is, there are no such things as little lumps or billiard balls or planets circling around the nucleus of an atom. That picture is dead. We still get it in books because it's something you can sort of imagine, but it's very misleading. There are no such things. So what are electrons? Well, that's where it begins to get difficult. What are electrons? Well, they are actually different when they're being observed and when they're not being observed. When they're being observed, they act, this is according to quantum physics, I'm not just making this up. When electrons are being observed, they are particles at a specific location. I mean, when you actually see one, it's a little particle which has hit a phosphor screen, you know, getting onto this screen. You can see on a photograph the impact, and it's a particle impact. You don't see the particle actually, but you see what the particle has done. You see where it's hit the screen. You say the particle hit it there. So they have a precise location. And in that sense, they're quanta, or particles. The trouble is when they're not being observed, they aren't particles. That's the real trouble. They are probability waves. What's a probability wave? That's what nobody knows. It's a mathematical construct, really. The wave, if you draw a wave like that, the wave gives you the probability that if you made an observation, you would find a particle at a particular place. Right? So it's not a real wave like something on the sea. It's not like that. It's a mathematical wave, and it gives you a probability that you might find a particle at a particular wave. In fact, slightly more technical, I'm not going to get very technical, but the square of the amplitude of a wave, that is from top to bottom of the wave, the square of the amplitude of a wave gives you the probability of the location at which a particle will be found if you have an experimental interference with the wave. Okay. So that's what an electron is. It's quite simple, really. No wonder they don't teach it in schools, though. They don't even teach it in first year physics. You don't do quantum until you're a postgraduate, you know, because it's much too difficult. So probability waves, you say, what does the world really consist of? Your electrons, your small billiard balls, have disappeared. They only exist when you observe them. And what's really there when you're not looking is probability waves. And probabilities aren't actualities, they're just probabilities. So if you say, where is the electron when we're not looking at it? Do you remember Bishop Berkeley, who said, where is everything when we're not looking at it? Berkeley had the view that to be is to be perceived. Anything which is only exists if it's being perceived. Color is a good example of this. We look around this room now, and we see lots of colors in this room. But in fact, if we left the room, if all of us left the room, there would be no colors in the room at all, because the realities with which physics deals have no color. Color is the product of an interaction between a light wave, that's a real wave, not a probability one, between a light wave and the electrochemical impulses in the brain which the light wave produces when it hits the retina of your eye. So color is, we might say, subjective. Now everybody agrees with that, don't you? Yes, I'm sure you do. So color doesn't exist in the external world. There are just waves of various frequencies. Depending on the frequency, when it hits the brain, you see a different color. And of course, if your visual apparatus is not attuned to those wavelengths, you wouldn't see these colors at all. And many animals see in black and white when they don't have, and some animals see infrared that we can't see at all. And Bishop Berkeley said, look, you see all these colors in this room, go out of the room, and what color will things be? No color at all. Color will not exist. Now, electrons are like that. They only exist if you're looking at them. Or more technically, if you're making an experimental interference, which collapses the probability wave into a particle. Right? But then you've got to look at it to see that. So if you're not looking, electrons don't exist. Only probability waves exist. Well, now, what this is coming up with is the view, accepted by many, but not all quantum physicists, the view that actually subatomic particles only exist when they're being looked at. Otherwise, they don't exist at all. Does anything exist? Let me give you a few quotations. You may not be believing me already, and it's going to get much worse. But let me give you some quotations from some very notable quantum physicists. John Wheeler, Nobel Prize-winning physicist, says, no elementary phenomenon is real unless it is observed. Just think about that. We know about all these particles, electrons, protons, neutrons, gravitons, hundreds of them, and Wheeler says none of them exist unless it's being observed. And people who talk about matter being the thing out of which minds somehow evolve are as wrong as they could possibly be, because matter is only in the mind. And if there weren't any minds, there wouldn't be any matter. Well, that's John Wheeler. You may think he's a nutcase, but Eugene Wigner, another Nobel Prize-winning physicist, says, study of the external world, he means in quantum physics, often called the new physics, because it's so different from Newton and even from Einstein, really. Eugene Wigner says, study of the external world leads to the conclusion that contents of consciousness are the ultimate reality. It's the same point. If you ask what is ultimately real, the answer is that which is a content of some consciousness. Now remember Bishop Berkeley again. Bishop Berkeley said, yes, things are real only when they're being observed. And you ask the question, well, what if nobody's looking? And Berkeley said, well, I'm a bishop, and I can tell you that God is always looking. So things are what they are because they're being observed by God. And if there wasn't a God, there wouldn't be anything. Von Neumann, yet another, they're all Nobel. All the people I'm going to quote are Nobel Prize winners, so they must be good at something. Von Neumann says, all real things are contents of consciousness. We see traces of it in CERN, in Geneva, marks left by particles which have been going round and round this vast tube at very fast speeds. But we never see the things themselves, and that's not surprising, because there aren't any. There is only a purely mathematical reality. And we haven't got a clue what that would be like. But whatever it's like, it's not material. So that's the end of materialism. And there's a little book by John Gribbin, perfectly respected scientific writer, and Paul Davies, mathematical physicist from Melbourne, Australia, called The Matter Myth, in which they just bring out the findings of this new physics. It's not anything like matter. Of course, Einstein contributed to this debate with his famous formula, which the one formula in physics that everybody knows, E equals mc squared, but nobody knows what it means. But what it does mean, all right, at the simplest level is energy equals mass, matter, times the square of the speed of light. Okay. In other words, mass, matter, and energy are convertible. Matter is only one form of energy. There are other forms of it as well. Now, that in itself is a world-shaking conclusion. Matter, far from being the fundamental reality, is just one form of energy. And there may be other forms. In fact, we do know some other forms that there are. There's antimatter, for a start. And there are other things, too. And from Heisenberg himself, and Heisenberg is really the great name, he formulated the first quantum theory. Since then, there have been others, Paul Dirac of Cambridge, and Schrödinger, who propounded the Schrödinger equations, which quantum physicists use. But Heisenberg is the originator, really. And he said, elementary particles, that's electrons, protons, neutrons, and so on, elementary particles form a world of pure possibilities. Atoms, he said, are not things. Right? So possibilities, not things. So from a quantum point of view, the world doesn't consist of very small things bumping into each other. In fact, you have to say there are no things. There are only possibilities, possibilities of perception. Now, what do you make of that? Well, one thing you could say, and people like Eugene Wigner do say, well, this shows that the whole of reality is a construct of mind. It's constructed by mind. And what mind could it be than the mind of God? So the mind of God becomes integral to science. It's not that you say, could we have an argument from physics to God? It's that physics is about God. That's what it's about. And people like Niels Bohr, there is a super intelligent cosmic mind, and matter only exists within that. And we see matter in a particular way as particles, elementary particles, and that depends on the nature of our consciousness. Quantum physicists don't all believe in God. They don't want to mislead you. And those who do believe in a cosmic mind might not call it God because they don't like what goes on in synagogues and churches and things like that. So they may say, I don't like the word God. Let's just talk about a cosmic mind. But to me, it's pretty close. And there are quantum physicists like John Wheeler, very famous quantum physicist, who says actually the Big Bang didn't exist until somebody thought of it. Right? The Big Bang wouldn't exist unless somebody thought of it, and that somebody, guess what, was God.
Who created the nothing? How can something come out of nothing? Where did the nothing come from? Does there have to be a beginning?
And according to quantum theory, there is no such thing as nothingness. You can have nothingness in quantum theory, but from that, things will arise. They will pop into existence and out of existence again.
So there can be a nothing.
So there's nothing, but nothing is not stable. Things come and go from nothingness.
Wait, so there are two kinds of nothing.
I'm going to talk about three.
He's got three. You got a fourth over here? Sorry. All right. I didn't know this. All right. We have more than one nothing. All right.
From Christian metaphysics is that God created the world out of nothing. So it's God plus nothing equals the world. And you take God out of the equation, and I'm all for that. But so now we have blank plus nothing equals the world. And what you put in the blank is the laws of nature, the laws of quantum field theory. And I think that actually in worrying too much about the problem of why there's something rather than nothing, and trying to find something to put in the blank where God used to be, you're actually still in thrall to Christian metaphysics. And I think you see the laws of nature, particularly the laws of quantum field theory, very much as divine commands.
So Jim, when did philosophers start weighing in on this?
Really with Leibniz. Why is there something rather than nothing? And by nothing, he meant a state in which there are no existence at all. There are no entities, there's no chaos, there's no space, no time, absolute nothingness. It's very difficult to grasp in the imagination. And there is a genuine question, why is there a universe rather than absolute nothingness?
It's my view that the simplest explanation is, there is no God. No one created the universe. This leads me to a profound realization. There is probably no heaven, and no afterlife either.
Here's what theoretical physicist Dr. Michio Kaku has to say.
I believe that Stephen is going a little bit too far in saying that because time itself was born at the instant of the Big Bang, therefore there is no God. If the universe is a bubble of some sort, it's expanding, that's the Big Bang theory, but in string theory, there are other universes out there. There's a multiverse of universes. Think of a bubble bath. These bubbles can collide, merge, or they can split apart into baby universes. And so we can talk, therefore, about a world before the Big Bang, a multiverse of universes. And then the question is, where did the multiverse come from? You could argue, therefore, that maybe you need a God to create the multiverse, or a creator to create string theory, perhaps.
I think the key point here is that these very laws that we're talking about, the laws that permit a universe to pop into existence, are simply, for most scientists, unexplained. But when you come to where do the laws of physics come from, most scientists say that's not part of science. You just have to accept them as a package. And in the show, Stephen Hawking gets very, very close to saying, well, where do the laws of physics come from? That's where we might find some sort of God. And then he backs away and doesn't return to the subject.
To get a universe from nothing, you've described the process, and I've heard it described before, but what you're starting with doesn't sound a lot to me like nothing. It sounds like the laws of quantum physics.
Yeah, it's a quantum foam, you know.
Yeah,
yes.
yeah. So that's not nothing. That's something.
That means something, but it's nothing in the sense of that there is no geometry in particular,
right.
Because our universe has a geometry.
Yes, there's no geometry, but it is a geometry generating mechanism.
In principle, yeah, there could be through the tunneling you generate this.
And
now, mind you, as I said from the beginning, this is all speculation.
Of course,
we don't know how this
we like
happened.
speculation. That's okay. But my concern is it's speculation and very interesting, and it may be right, but it's not answering the question. The question is, why is it something rather than nothing? And you're
and my answer is that I do not know. I only can say that
because you're starting with,
according to the laws of physics that I know, this was possible.
Right.
But why it is, I don't know.
Right, but the laws of physics, if we have quantum physics, which is the generator, whether it's the indeterminate principle or whatever it is that is part of the quantum physics, is very complicated. But it is complicated. It is something, and it's a lot of stuff. Maybe it'll be reduced down to something even more simple in string theory, or who knows. But quantum field theory is a lot of things going on to make that. And so if you start with that, and you have a mechanism to generate a universe with geometries and everything else, but you're starting with something pretty rich.
Right. Well, you start with some laws.
Some laws.
Yes.
Yeah.
So you're right. So the question is, why are there some laws? And again, I don't know the answer to that.
Alex, literally all my life, I've been obsessed by the question of why there's anything at all. And you've addressed certainly one of the subset questions, and why this universe, how this universe can emerge literally from the nothingness of the laws of physics. So quantum mechanics gets you from 0 to this small size, and once you get to this small size, then you're able to use general relativity and Einstein theory to generate all the rest.
Right.
Now, this is remarkable and awesome, but it is not something from nothing, because you're starting with the laws of quantum physics, you're starting the laws of general relativity. I mean, there's a lot of somethings there.
So what I'm starting with are indeed the laws of physics, or general relativity and quantum mechanics. And of course, and these laws are assumed to exist in some sense, in some Platonic sense, even prior to the universe, although prior I should put in quotation marks because there is no time. And the question, of course, is an extremely intriguing question of why these laws, who gives the laws,
It's a deep mystery, and I don't have much to say about that. I would like to.
Paul, on multiple universes, I've talked to all of our friends, everybody that you and I know who have originated and talked about multiple universes. It's enormously exciting. It's the most mind-expanding thing that I've ever confronted in my life. Everybody assumes that it's real, it's just how it works. But is it real?
I usually say 2 cheers for the multiverse, because there are good reasons of physics and cosmology for supposing that what we see may not be all you get, that there may be other regions of space and time that could be different. So it's not an unreasonable speculation. However, it falls far short of being a complete theory of existence, which is often presented as, that as if, well, if there's a multiverse, we can forget about all the mysteries of the universe because it's all explained. Everything's out there somewhere, end of story. Well, it's simply not true, because to get a multiverse, you need a universe-generating mechanism. Something has got to make all those big bangs go bang. So you're going to need some laws of physics to do that. All of the theories of the multiverse assume quantum mechanics, quantum physics, to give the element of spontaneity to make the bangs happen. They assume pre-existing space and time. They assume the normal notion of causality, a whole host of things. You write down a list, there's about 10 different basic assumptions they have to make to get the theory to work. And you can say, well, where have they all come from? What about these meta-laws that generate universes and impose effective local bylaws, as Martin Rees would call it, upon these universes? What is this distribution mechanism? How does that work? Where do those rules come from? So all you've done is shift the problem of existence up from the level of universe to the level of multiverse, but you haven't explained it. So
but if it's real, you certainly have described what a new reality is. But how strong can we believe in that reality? Even if it's hard, even if it doesn't explain everything, is that what there is that we have to explain?
Right. Now, the big problem is how do we test? How do we test this idea? It's all very well saying there are all these other universes, but is there any way of testing it? Well, it turns out there are ways of, in some sort of weak sense of testing it. We can falsify it. If you claim that a particular feature of the universe is due to the fact that only a handful of these universes in the multiverse are inhabited by beings such as ourselves who can observe these things. If you say that, that it's selected for that reason, this particular feature, there are certain statistical tests that you can apply, and if this a particular feature fails those statistical tests, you can say that's evidence against the multiverse. But it is very weak. I suppose for me, the main problem is that what we're trying to do is explain why the universe is as it is by appealing to something outside of it. In this case, an infinite number of universes outside of it. And the problem about the multiverse is not that such a thing is unreasonable scientifically. It's not. It's very reasonable. It's that how on earth are we going to know about these other universes? They're not directly observable because in the fashionable view based on eternal inflation, these other universes are being conveyed apart faster than they're expanding. And so even in principle, you can't see across the gulf between them. It's possible you can apply some weak statistical tests to the fact that the universe we see may have certain features which are there because we exist, that is, that only some of these universes within this multiverse support life. And so obviously we're going to see a universe which has those features which are important for life. And there are statistical tests one can apply there. But, you know, it really is pretty feeble. And so I think the main objection, it's just a philosophical, not a scientific objection, is that what you're doing is trying to explain the universe we see by appealing to, in this case, an infinite number of universes that we don't see, appealing to something outside of the universe. And that is no better than traditional theology, which, and as a matter of fact, I believe that if somebody did a proper mathematical analysis, they would find that the complexity of the explanation of the multiverse, an infinite number of universes we don't see, is the same as the complexity of the explanation of traditional theology, an infinitely complex God outside the universe that we don't see. They're really the same thing, in different language.
So, how sure are we that the universe is the way that string theory describes it? Is the world really made up of strings and membranes, parallel universes, and extra dimensions? Is this all science or science fiction?
Well, the question we often ask ourselves as we work through our equations is this just fancy mathematics, or is it describing the real world?
These exercises in our imagination and mathematics are all, at the end of the day, subjected to a single question. Is it there in the laboratory? Can you find its evidence?
String theory and string theorists do have a real problem. How do you actually test string theory? If you can't test it in the way that we test normal theories, it's not science, it's philosophy. And that's a real problem.
Strings are thought to be so tiny, much smaller than an atom, that there's probably no way to see them directly.
I think it's actually stronger than that.
Okay.
That what is referred to as M theory isn't even a theory. Yes. It's a collection of ideas, hopes, aspirations.
Exactly.
It's not even a theory. And I think the book is a bit misleading in that respect. It gives you the impression that here is this new theory which is going to explain everything. It's nothing of the sort. It's not even a theory, and it certainly has no observational... partly it's this 10 to the 500 you refer to.
This is one of the interesting aspects of what he appears to be saying, is that M theory shows that the universe can create itself, so to speak, out of nothing. I mean, is that something which science can ever really tell us or be definitive? Take
It's certainly not doing it yet. I think the book suffers rather more strongly than many. I mean, it's not an uncommon thing in popular descriptions of science to latch on to some idea, particularly things to do with string theory, which have absolutely no support from observation. They're just nice ideas that people have tried to explore.
But they will always remain theoretical. I mean,
always is too strong. It may well be they just be refuted, but even that is something which is they're very far from any kind of observational
or testability.
Tests. Yes, they're hardly science.
More abstract argument for the existence of God is the first cause argument. Let's just look at the simple, basic, intuitive, natural, commonsensical form of it. I think we all have to become rather clever in order to doubt it or to dispute it, because it's based on an instinctive mind that we all share, the instinct that says everything needs an explanation. Nothing just is, without a reason why it is. Everything that exists has some adequate or sufficient reason why it exists. Philosophers call this the principle of sufficient reason. We use it every day, in common sense and in science, as well as in philosophy. If you saw a rabbit suddenly appear on this empty table, you would not blandly say, "Hi there, rabbit, you came from nowhere, didn't you?" No, you'd look for a cause. You would assume there has to be some cause. We never deny the principle of sufficient reason itself. No one believes the pop theory, that things just pop into existence for no reason at all. Perhaps we will never find the cause, but there must be a cause for everything that comes into existence. Now, the entire universe is a vast interlocking chain of things that come into existence. Each of these things must therefore have a cause. My parents caused me, my grandparents caused them, etc. But it is not that simple. I would not be here without billions of causes, from the Big Bang through the cooling of the galaxies and the evolution of the protein molecule to the marriages of my ancestors. The universe is a vast and complex chain of causes. Now, does the universe as a whole have a cause? Is there a first cause, an uncaused cause, an eternal cause, a transcendent cause of the whole immanent chain of causes? If not, then there is an infinite regress of causes with no first link in the great cosmic chain. If so, then there is an eternal, necessary, independent, self-explanatory being with nothing above it, nothing before it, nothing supporting it. It would explain itself as well as everything else. For if it needed something else as its explanation, its reason, its cause, then it would not be the first and uncaused cause. Such a being could be called God. If we can prove there is such a first cause, we will have proved that there is some sort of God. Now, why must there be a first cause? Because if there isn't, then the whole universe is unexplained, and we have violated our principle of sufficient reason for everything. If there is no first cause, each particular thing in the universe is explained by some other thing, but the universe as a whole is not explained. Everyone and everything in the universe says in turn, don't look to me for the final explanation. I'm just an instrument. Something else caused me. But if that's all there is, beings that say that, then we have an endless buck-passing universe. God is the one who says the buck stops here. One more analogy. Suppose I tell you there is a book that explains everything you want explained. You want that book very much. You ask me whether I have it. I say, no, I have to get it from my wife. Does she have it? Well, no, she has to get it from a neighbor. Does he have it? No, he has to get it from his teacher, who has to get it from, etc., ad infinitum. No one actually has the book. In that case, you will never get it. However long or short the chain of book borrowers may be, you will get the book only if someone actually has it and does not have to borrow it. Well, existence is like that book. Existence is handed down the chain of causes, from cause to effect. If there is no first cause, no being who is eternal and self-sufficient, no being who has existence by his own nature and does not have to borrow it from something else, then the gift of existence can never be passed down the chain to others, and no one will ever get it. But we did get it. We exist. We got the gift of existence from our causes down the chain, and so did every actual being in the universe, from atoms to archangels. Therefore, there must be a first cause of existence, a God. The thing to do is to return to what is sure and clear, the intuitive point I began with. Not everyone can understand all the abstract details of the first cause argument, but everyone can understand its basic point. C.S. Lewis puts it this way, I felt in my bones that this universe does not explain itself.
Why does anything at all exist? Gottfried Leibniz wrote, the first question which should rightly be asked is, why is there something rather than nothing? He came to the conclusion that the explanation is found in God. Someone might say, if everything that exists needs an explanation, what about God? Doesn't he need an explanation? And if God doesn't need an explanation, then why does the universe need an explanation? To address this, Leibniz makes a key distinction between things that exist necessarily and things that exist contingently. Things that exist necessarily exist by necessity of their own nature. It's impossible for them not to exist. Many mathematicians think that abstract objects like numbers and sets exist like this. They're not caused to exist by something else, they just exist by necessity of their own nature. Things that exist contingently are caused to exist by something else. Most of the things we're familiar with exist contingently. They don't have to exist. They only exist because something else caused them to exist. There's no reason to think the world around us had to exist. If the universe had developed differently, there might have been no stars or planets. It's logically possible that the whole universe might not have existed. It doesn't exist necessarily, it exists contingently. If the universe might not have existed, why does it exist? The only adequate explanation for the existence of a contingent universe is that its existence rests on a non-contingent being, something that cannot not exist because of the necessity of its own nature. It would exist no matter what. So, everything that exists has an explanation of its existence, either in the necessity of its own nature or in an external cause. But what about our second premise? Is it reasonable to call the explanation of the universe God? Well, what is the universe? It's all of space-time reality, including all matter and energy. It follows that if the universe has a cause of its existence, that cause cannot be part of the universe. It must be non-physical and immaterial, beyond space and time. The list of entities that could possibly fit this description is fairly short, and abstract objects cannot cause anything. Leibniz's contingency argument shows that the explanation for the existence of the universe can be found only in the existence of God. Or, if you prefer not to use the term God, you may simply call him the extremely powerful, uncaused, necessarily existing, non-contingent, non-physical, immaterial, eternal being who created the entire universe and everything in it.
If one asks what caused God, the answer is that nothing could bring into being a reality which wholly transcends space-time and which is self-existent. To fail to grasp such an idea is to fail to grasp what God is. Everything that begins to exist has a cause. Something cannot come into being out of nothing. This is rooted in the metaphysical idea that being cannot come from non-being. Out of nothing, nothing comes. That Hawking hasn't even begun to address the question, why is there something rather than nothing? For nothing, in his vocabulary, does not have the traditional meaning of non-being, but rather means the quantum vacuum. Hawking and Mlodinoff's equivocal use of terms is painfully evident in their interview with the American television host Larry King on his program. Here is how it went. Hawking: gravity and quantum theory cause universes to be created spontaneously out of nothing. Larry King: who created the nothing? Where did the nothing come from? Mlodinoff: according to quantum theory, there is no such thing as nothingness. Now, in this ridiculous exchange, Hawking is using nothing to refer to the quantum vacuum, while Mlodinoff is using it to mean non-being. And they avoid the tough question, why is there something rather than nothing, only by equivocating on the use of their terminology. Despite Hawking and Mlodinoff's constant sniping at religious belief throughout their book, I think there is actually genuine profit in it for religious believers, especially for those interested in natural theology. For the authors affirm and argue for an absolute beginning of time and the universe, which points ineluctably to a transcendent cause beyond the universe. That the evidence of contemporary cosmology actually renders God's existence considerably more probable than it would have been without it. This is not to make some sort of naive claim that contemporary cosmology proves the existence of God. There is no God of the gaps reasoning here. Rather, I'm saying that contemporary cosmology provides significant evidence in support of premises in philosophical arguments for conclusions having theological significance. For example, the key premise in the ancient Kalam cosmological argument that the universe began to exist is a religiously neutral statement which can be found in virtually any textbook on astronomy and astrophysics. It is obviously susceptible to scientific confirmation or disconfirmation on the basis of the evidence. So, to repeat, one is not employing the evidence of contemporary cosmology to prove the proposition that God exists, but to support theologically neutral premises in philosophical arguments for conclusions that have theistic significance. The Kalam cosmological argument. 1. If the universe began to exist, then there is a transcendent cause which brought the universe into existence. 2. The universe began to exist. 3. Therefore, there is a transcendent cause which brought the universe into existence. By the universe, I mean that reality which is studied by contemporary cosmology. That is to say, all contiguous physical reality which currently takes the form of space-time and its contents. I take it that one is obviously true. Rather, the truly controversial premise is two. Traditional supporters presented philosophical arguments in support of two, which for me constitute its primary warrant. But they're not the subject of tonight's debate. Rather, what's emerged during the 20th century is a remarkable empirical confirmation of the second premise from the evidence of astrophysical cosmogony. Two independent but closely interrelated lines of physical evidence support premise two: evidence from the expansion of the universe and evidence from the second law of thermodynamics. In saying that the cosmogonic evidence confirms two, I am not saying that we are certain that two is true. Too many people mistakenly equate knowledge with certainty. When they say that we do not know that the universe began to exist, what they really mean is that we are not certain that the universe began to exist. But of course, certainty is not the relevant standard here. The question is whether two is more plausible in light of the evidence than it's contradictory. Professor Carroll reminds us, science isn't in the business of proving things. Rather, science judges the merits of competing models in terms of their simplicity, clarity, comprehensiveness, and fit to the data. Unsuccessful theories are never disproven, as we can always concoct elaborate schemes to save the phenomena. They just fade away as better theories gain acceptance. Science cannot force you to accept the beginning of the universe. You can always concoct elaborate schemes to explain away the evidence. But those schemes will not fare well in displaying the aforementioned scientific virtues. Even many who have expressed skepticism about premise two admit that it is more plausibly true than not. For example, in my recent dialogue with Lawrence Krauss, he volunteered, "I bet our universe had a beginning, but I am not certain of it. Based on the physics that I know, I'd say it is a more likely possibility." This is to admit precisely what cosmologists like Alexander Vilenkin have contended all along, that the evidence makes it more likely than not that the universe began to exist. Consider first evidence from the expansion of the universe. The standard Big Bang cosmogonic model implies that the universe is not infinite in the past, but had an absolute beginning a finite time ago. Although advances in astrophysical cosmology have forced various revisions in the standard model, nothing has called into question its fundamental prediction of the finitude of the past and the beginning of the universe. Indeed, as James Sinclair has shown, the history of 20th century cosmogony has seen a parade of failed theories trying to avert the absolute beginning predicted by the standard model. Meanwhile, a series of remarkable singularity theorems has increasingly tightened the loop around empirically tenable cosmogonic models by showing that under more and more generalized conditions, a beginning is inevitable. In 2003, Arvin Bord, Alan Guth, and Alexander Vilenkin were able to show that any universe, which is on average in a state of cosmic expansion throughout its history, cannot be infinite in the past, but must have a beginning. In 2012, Vilenkin showed that cosmogonic models, which do not fall under this condition, including Professor Carroll's own model, fail on other grounds to avert the beginning of the universe. Vilenkin concluded, none of these scenarios can actually be past eternal. All the evidence we have says that the universe had a beginning. The Born-Guth-Vilenkin theorem proves that classical spacetime, under a single, very general condition, cannot be extended to past infinity, but must reach a boundary at some time in the finite past. Now, either there was something on the other side of that boundary or not. If not, then that boundary is the beginning of the universe. If there was something on the other side, then it will be a non-classical region, described by the yet-to-be-discovered theory of quantum gravity. In that case, Vilenkin says, it will be the beginning of the universe. Think about it. If there is such a non-classical region, then it is not past eternal in the classical sense, but neither can it exist literally timelessly, akin to the way in which philosophers consider abstract objects to be timeless, or theologians take God to be timeless. For this region is in a state of constant flux, which, given the indiscernibility of identicals, is sufficient for time. So even if time as defined in classical physics does not exist at such an era, some sort of time would. But if the quantum gravity era is temporal, it cannot be extended infinitely in time. For such a quantum state is not stable, and so would either produce the universe from eternity past or not at all. As Anthony Aguirre and John Kihayas argue, it is very difficult to devise a system, especially a quantum one, that does nothing forever, then evolves. A truly stationary or periodic quantum state, which would last forever, would never evolve, whereas one with any instability will not endure for an indefinite time. Hence, the quantum gravity era would itself have to have had a beginning in order to explain why it transitioned just some 13 billion years ago into classical time and space. Hence, whether at the boundary or at the quantum gravity regime, the universe probably began to exist. Consider now the evidence of thermodynamics. According to the second law of thermodynamics, entropy in a closed system almost never decreases. Given the naturalistic assumption that the universe is a closed system, the second law implies that given enough time, the universe will come to a state of thermodynamic heat death, whether cold or hot. Given that the universe will expand forever, it may never reach a state of equilibrium, but will grow increasingly cold, dark, dilute, and dead. But then the obvious question arises: why, if the universe has existed forever, is it not now in a cold, dark, dilute, and lifeless state? P.C.W. Davies gives the obvious answer. The universe can't have existed forever. We know there must have been an absolute beginning a finite time ago. The universe's energy, says Davies, was simply put in at the creation as an initial condition. By contrast, Professor Carroll's solution to the problem confronts serious obstacles. He imagines that the overall condition of the universe is a state of thermal equilibrium, a sort of de Sitter space, but that random fluctuations spawn baby universes which pinch off to become wholly independent spacetimes. We find ourselves in one such baby universe in a state of disequilibrium. Let me raise two concerns about this model. First, not only are the production mechanisms of such baby universes admittedly conjectural, but such a scenario violates the so-called unitarity of quantum theory by allowing irretrievable information loss from the mother universe to the babies. Stephen Hawking, apologizing to science fiction fans everywhere, came to admit, "There is no baby universe branching off. As I once thought, the information remains firmly in our universe." Second, Professor Carroll's solution provides no convincing answer to the Boltzmann brain problem. Since the mother universe is a de Sitter space in which thermal fluctuations occur, and since baby universes grow into de Sitter spaces themselves, there's no explanation in the model why there exists a genuine low entropy universe around us, rather than the mere appearance of such a world, an illusion of isolated brains which have fluctuated into existence out of the quantum vacuum. These and other problems make Professor Carroll's model less plausible than the standard solution that the universe began to exist with an initial low entropy condition. Skeptics might hope that quantum cosmology might serve to avert the implications of the second law of thermodynamics. But now, a new singularity theorem formulated by Aaron Wall seems to close the door on that possibility. Wall shows that given the validity of the generalized second law of thermodynamics in quantum cosmology, the universe must have begun to exist, unless, as in Professor Carroll's model, one postulates a reversal of the arrow of time at some point in the past, which, he rightly observes, involves a thermodynamic beginning in time, which would seem to raise the same sorts of philosophical questions that any other sort of beginning in time would. Wall reports that his results require only certain basic concepts so that it is reasonable to believe that the results will hold in a complete theory of quantum gravity. Thus, we have good evidence, both from the expansion of the universe and from the second law of thermodynamics, that the universe is not past eternal, but had a temporal beginning. So, the second premise of the Kalam cosmological argument receives significant confirmation from the evidence of contemporary cosmology. But in one sense, the history of 20th century cosmology has been the history of one failed attempt after another to avert the absolute beginning predicted in the standard Big Bang model. We've seen the steady state model, we've seen oscillating models of the universe, we've seen vacuum fluctuation models, chaotic inflationary models, quantum gravity models, most recently the so-called ekpyrotic cyclical models of the universe, all of these attempting to avoid the absolute beginning predicted in the standard model. And one after another, these theories have either been falsified by the data or shown to be mathematically inconsistent, or else they have been shown to imply the very beginning of the universe that they sought to avoid. So I think that the prevailing view among contemporary cosmologists is that the universe cannot be eternal in the past, but that there is a past space-time boundary that represents the absolute beginning of the cosmos. Paul Steinhardt and Neil Turok's so-called brain cosmology, which is an attempt to exploit string theory to develop an eternally oscillating universe in higher dimensions. And they tried to extend this infinitely into the past. But what was discovered in 2003, in the fall of that year, by three cosmologists, Alexander Vilenkin, Arvind Borde, and Alan Guth, the father of inflationary cosmology, through their theorem, they were able to demonstrate that even these models cannot be extended infinitely into the past, but that there has to be a past boundary at some point that represents the beginning of the universe. So even these brain cosmologies and higher dimensional cosmologies, which are really very metaphysical in character, have been shown to be non-infinitely extendable into the past. That is to say that they must have a past boundary. The very nature of science is that its results are always provisional. They're always tentative. Well, there are other versions of the cosmological argument that don't depend on the universe having a beginning. For example, the great German philosopher Leibniz held that even if you have an eternal universe in the past, that doesn't explain why there is any universe. So for Leibniz, the eternality or infinitude of the past was irrelevant to the question of whether there is a metaphysically necessary being that explains why the universe exists. But this would be relevant, though, to the Kalam cosmological argument, because if it turned out to be correct and could be extended to past infinity, then it would not be true, at least scientifically that you can give good evidence that the universe began to exist. You would still have all of the philosophical arguments in place against an infinite regress. And doesn't there need to be some sort of an ultimate explanation of reality?